everyone. Great speaking here at DevConf again, one of the best conferences ever. My name is Itamar holder, and I'm a Kubernetes maintainer and a Kubernetes developer. And this talk is about what the swap, so swap in Kubernetes, current status and future plans. And when I first wrote this, I just thought to myself, let's try it out and see what happens. So I took a node with swap enabled, started kubelet, and the whole thing just exploded immediately, bursted into flames. And I was pretty surprised by that, because, I mean, what the swap is so difficult about it? Can we just schedule a pod onto a node with swap enabled and let it swap if it has to? But first let's talk about a few use cases or why swap is even important. Because there is a common misconception that swap is a thing of the past and it doesn't matter nowadays. There is a very interesting piece by Chris Don that's called In Defense of Swap, and there it basically says, swap is a hotly contested topic. Many see it as useless, a relic of a time where memory was scarce and disks were a necessary evil to provide space for swapping. So yeah, a lot of people feel that way about swap. Another quote from the kernel documentation is that you might think that swap is unnecessary, but a significant number of pages may only be used for initialization and then never used again. And this actually happens in a lot of cases. So, for example, language runtimes that load all the source code into memory and then never touches it again, or processes that reserve memory in advance for things like custom OM handling and things like that, or maybe even like shared libraries. It's common to import a library, use a function just somewhere for initialization, and then never touch it again. So yeah, that's pretty common. But at least in these kind of cases, it's still pretty easy to understand what's the amount of memory that's used only for initialization. And so let's talk generally about monitoring and profiling the memory consumption of pods on Kubernetes. So let's take this graph as an example. In order to understand which limits and requests of memory we should set to the pod, we let it run, use tools like Prometheus or something like that to profile and monitor it. And as you can see, at least in this graph, there is some kind of a baseline level of memory, and the request will be set somewhere around here, maybe a bit above if we want to be more conservative about it. And then there are memory spikes once in a while, and the limit will be set like approximately at the highest spike. Again, maybe a bit higher if we want to be more conservative. But this case is pretty easy, so we're going to complicate stuff a bit. So first of all, a question to the crowd. So what happens when memory limits are met, or when pod reaches the memory limits? Somebody brave from the crowd. Yeah. Kill. Okay, thank you for this answer, because that's the non-accurate answer. But that's a common belief, so I don't blame you. The accurate answer is that before the pod dies, the kernel will put the pod under a heavy reclaim pressure and will do anything it can to actually free the memory, for the memory to go below the limits. So usually what the kernel does is freeze open files that could be flushed back to disk, caches, kernel structures, and stuff like that. But the reality is that usually it's not a huge amount of memory that could be reclaimed. So you're practically right. I mean, if you reach the limit, you usually would get unkilled right away. But with swap, it's different, because with swap, we can actually reclaim gigs of memory, which is a game changer, and it's really crucial to save the pod from crashing, basically. So let's speak about another case. So on the container level, we could have a graph that looks something like that. So the consumption of memory is predictable, it's constant, nothing happens. And then there is a temporary, rare, and unpredictable memory spikes once in a while. When this happens, like, how do you set limits? That's problematic, because you can set limits like way higher than what your program will usually consume. Actually, if we set limits this way, then once we reach the limit, then the kernel could reclaim memory and basically save it from crashes. And that's a thing that's pretty common in many cases. So for example, in machine learning, another example is the fork exec pattern, which is used, for example, by interpreters like Ruby on Rails. So between the fork and exec, you would double your memory temporarily just for a second. And so that's one of the use cases. We can also look at it at the node level. So let's say that we have a cluster, and our nodes are relatively small. We have like 30 gigs RAM capacity. And let's say that we have to schedule a cron job once in a while, let's say once a week, that we do something, and we know it consumes about 20 gigs of memory. So without swap, basically, we can't assume that we have 20 gigs free on a node. What will probably happen is that it will get scheduled, some pods will die, rescheduled to somewhere else, and that's just a wasted cost that is unnecessary. Again, with swap, a few gigs could be swapped away. We would, again, schedule it to the most quiet hours, so it's safe to assume that nothing else needs to happen here. I bet some of you are asking yourself, well, why shouldn't we scale in those situations? And it's not always possible. So, for example, for cost reasons, and like in on-prem bare metal environments, it also might be not even possible to dynamically add nodes to the cluster. Another use case is fast storage, like NVMe. So this is especially important for computing on the edge. Then you have a relatively, again, small server, and if you have NVMe, it could add very fast memory that would be added to the edge, which is very important in these cases. And by the way, some servers even today have NVMe storage, and this could just be utilized to add practically more RAM to the system. Another example is very, very small servers. So I'm talking about less than 4 gigs of memory. If that's what you use, then kubelet will start being unstable. But again, a lot of things are used only for initialization and could be swapped away afterwards, so that this way you can make use of very, very small servers. And another one is third-party application. So for example, UMD, and if you're not familiar with it, it's a user space daemon that's created by Facebook that basically proactively tries to prevent the kernel's killer to be invoked. And this is a very good technology that cannot currently be used with Kubernetes because UMD requires swap to operate correctly. So yeah, as you can see, there are tons of use cases. But what interested me specifically coming to this is KubeVirt, right? So as I said, I'm a KubeVirt maintainer, and what KubeVirt basically does is allows you to run virtual machines on Kubernetes as a first-class citizen. And I'm not going to talk about its whole architecture now, but the main trick that you need to understand is that the guest runs inside a container. That's basically the trick. But realistically, it looks something like that. So in the container, we have the guest itself and another virtualization infrastructure, like the hypervisors and some other stuff that we need in order for the guest to operate and run. But if we're looking on a node level, it looks a bit something like this. And as you can, because we have many VM instances running there, and as you can see, a lot of the data is duplicated here. So first of all, the virt infra. Again, I think that a lot of the pages that are used for initialization never used again. So that's what we talked about before. But the guest OS is also a thing because unlike containers, which have a really thin dependency layer, virtual machines have a huge dependency layer, which is all of the operating system, including all of its pages, all of the memory, which is usually not used, or at least not the entirety of it is being used. And we thought about how to solve this issue. And we thought about swap, of course. Another mechanism is called KSM, which stands for kernel same page merging. And the idea is basically if there is a page that is duplicated across the system, it hasn't been recently used, it's going to be merged, going to be set as read-only and treated as a copy and write matter. So the dangerous part about KSM is that if a page is being duplicated, and then at the same time, many instances would write to this page, it would be needed to duplicate again. And in this scenario, we would have a huge memory spike that's sudden, and swap acts as another safety net to help us from crashing everything. So how do we set memory requests? Basically, there is the guest memory and the infrastructure overhead, and the memory request equals to the sum of those. What we can do is reduce a bit the memory request, and we call that overcommitment. That basically allows us to increase the density of virtual machines on a node, and we basically assume that some of the pages would be reclaimed, either merged or swapped away. So the both mechanisms work really great together. So in this example, let's say that the orange pages here are duplicated and nobody touches them. They will be merged into a single page. Once VMs start writing to it, it will be duplicated again. And then the pages that haven't been used in a while will be swapped away. So these two work really good together. And as you can see, we have tons of use cases here that are relevant not only to KubeVirt. And I spoke to my managers about it, and I said that I think that we should implement it in upstream Kubernetes. And my manager reacted something like that. So the reason is that overcommitment support is very, very important for Red Hat virtualization, and in Kubernetes, features are moving slowly. There are a lot of eyes looking at every change you do. People are coming to it from many different companies, and it's very, very hard to gain a broad consensus basically on everything. So yeah, I said, let's do it anyways. And let's return to this point. What the swap is so difficult about it? So let's get back to the alpha days. That's how it looked like mostly. So it was rotten, abandoned. The developer that started it left the community years ago. There was no interest around it. It has no priority. Nobody was working on it. And basically, it didn't work, right? It didn't support V2. It had tons of problems, and nothing really worked. So I started looking into it, and I've realized really early on that one of the most important things about swap is how to limit swap access. Because the thing is that swap is a system property, and swap abuse could lead to node-level instabilities. And that's very scary, and we need a good way to limit swap access to pods. So initially, at these alpha days, the KEP suggestion was to simply add it to the pod API. So just like you request memory, you would be able to request swap space. But this is a very bad idea for multiple reasons. So first of all, assigning memory is hard. Assigning swap is almost impossible. It's a system-level resource, as I said. So a pod can swap pages away because of external reasons that are not related to what the pod is doing by any means. Another thing is, so if that's the case, how is it even possible to profile it? How does it even possible to reason about it? Another thing is that swap is machine dependent. The ratio between the swap size and the RAM size is different between every machine. And that the swap space is backed by different storages in different machines. But maybe the most important point here is backward compatibility. Because adding stuff to the pod API is both a hard thing to do in terms of gaining consensus to do it. But after you add fields to the pod API, you can't remove them. I mean, you can remove them easily, and by saying that, I mean you can't remove them ever, basically. So for example, spec node name, a notorious example for a horrible field that everybody agrees is super bad, but nobody wants to remove it just for backward compatibility reasons. So we have to be very, very careful about it. So my idea around it was that we would have no APIs whatsoever. And more generally, what I said is that we should frame this cap as basic swap enablement. This way, we could actually try to GA in the near future, because there are a lot of stuff that could be extended with swap, and there are a lot of different angles that we can extend. But let's not do it now, right? Let's have some swap enablement, and then let's have follow-up caps that would address different problems around swap and would extend it. So one of the follow-up caps will be customizability and APIs. But in this cap, I wanted to not present any APIs at all. So it basically means that the limits should be auto-calculated. But how can we do that? So in the alpha days, there were two swap behaviors, they're called. One of them was unlimited swap. Basically, every container can use how much swap they want. And as we said, that's dangerous because an abuse could lead to node level stability. This behavior was eventually dropped and replaced with something that is called NodeSwap. That means that no pod can swap. But the limited swap is actually more interesting. And the original idea was to set swap limit the same as memory limit. And again, this doesn't really make sense because of a few reasons. So first of all, we give the control to the user, right? So basically, the user or the pod owner is the one who determines what are the restrictions around swap. And again, that's too dangerous. Another issue here is that order of scheduling matters, right? Because if, let's say that there are two pods with the same memory limit, and the memory limit is so high that it's like higher than the swap capacity. So basically, there is no limit, right? So the first pod will be scheduled, can use all swap memory. The second pod will be scheduled, and it won't be able to use any swap memory. And that's really bad. We want that, the order of the pods being scheduled to a node wouldn't change anything. Another thing is that it's not correlated to the node's capacity, which is a point that I'll talk about a bit later. So a quick reminder about quality of service. So in Kubernetes, we have three quality of service classes. So best effort is the first one. Basically, it doesn't provide any information about the resources it's going to use. Guaranteed is kind of the opposite. It specifies both requests and limits to both CPU and memory, and they have to be equal. And burstable is basically everything else. So let's examine these classes and see for which one of them it makes sense to actually swap. So guaranteed, not really, right? Because the whole concept is that it's guaranteed that the memory would wait for you there and will not go away. And these are usually high priority pods. So it doesn't really make sense to use swap in this case. Best effort also, it's too dangerous. Basically, we have no information about it, so it's very hard to understand what the limit should be. And another point is that it's okay to kill them if needed, right? That's the meaning of best effort. Like, you should run them if you can, and if not, that's fine. And so burstable is actually a perfect fit for swapping, because basically it means that we have kind of baseline of memory that we can use, but we are aware of the fact that it would burst once in a while, and that's fine. And another point is that most of the workloads anyways are burstable, I think, right? Because it just covers like most of the cases. The first decision is that only burstable pods would be able to swap. Now, another question to the crowd. Let's say that we have a node with 10 gigs of memory, and we have a pod that requests 5 gigs of memory and limits itself to 20 gigs of memory. Can the pod be scheduled to the node? You're nodding yes, and you're right this time. What I want to emphasize here is that only requests are relevant for scheduling. Limits don't have anything to do with it. And so the important insight from that is that possibly the sum of all the limits of the pods scheduled to a node may be greater than the node's memory. But necessarily, the sum of all the requests is smaller or equals to the node's capacity. And that's very important. And so without further ado, let's talk about the actual solution. So on the one hand, we're going to take RAM and swap capacity into account. And on the other hand, we're going to take memory request into account. Now let's say that our node has 10 gigs of memory and 2 gigs of swap. So if this pod is going to be scheduled to the node, you have the formula at the bottom left, but I think it's more interesting to understand the idea here. And the idea is that 2 gigs of memory is 20% of the RAM's capacity. So this pod will be limited to 20% of the swap capacity. So it's basically correlated between them. That way we can, we solve all the problems that we talked about before. Who schedule first to the node doesn't matter at all. This way you don't need to think about what's the size of swap, and you don't need to provide any values at all, and it just sort of makes sense. By the way, the limits are here again, just to emphasize that they don't have anything to do with it. While this problem was very significant, a lot more was done. So for example, monitoring in alpha looked something like that. I had to start bashing in the pod and start printing out cgroup files, contents, and stuff like that. So basically there was any monitoring support. Now there is monitoring support via the stats summary endpoint, which is basically used by Prometheus and other monitoring tools. There's also support for VPAs or vertical pod autoscalers with the metric resource endpoint. And that's also pretty cool that autoscalers can take it into account. But still, like people demanded that, this is for software, right? It's for VPAs and for monitoring tools. The community demanded that users will easily find out which nodes have swap and how much swap capacity do they have. We thought about doing something like this with kubectl describe node, but people didn't really like it because it seems from this as if you can request it in the pod API, which might be confusing. And so eventually we'll probably do something like that, a node condition that will specify whether swap is enabled and which swap behavior is used. This is still work in progress, so don't take it too seriously. Another really big thing was memory-backed volumes. So, for example, secrets and mtdir volumes that are backed by memory cannot swap to disk. These are two different cases. With secrets, it's a matter of security, right? Kubernetes guarantees that secrets will always be on RAM, will not swap to disk ever. And with mtdir, it's more about performance. So pods can use mtdirs that are backed by memory to have pages that are there at demand and wouldn't be on disk. And so this was a really hard problem because basically all of the limitations that I talked about are implemented with cgroups. And cgroup is about processes. Now, the volumes are mounted by kubelet and shared with the container. But the thing is that the volumes can be populated with data that no process can consume. So for example, let's say that processes start out and just dump data into this mtdir volume and just don't ever consume that data. Because, again, it's outside of the process's consumption. Nothing limits these pages from being swapped to disk. And this was a very hard problem. We started thinking about all sorts of crazy solutions. So currently, kubelet uses tempfs to mount these volumes. We thought about other alternatives like ramfs, which the difference between ramfs and tempfs is that the pages there cannot swap, so that works for us. But on the other hand, it's very old. It's unconfigurable entirely. So yeah, that was a problem. Another alternative was using a thing called RBD, which stands for RAM block device. But again, it was very hard to configure and very different than what kubelet is doing now. And the thing is that in order to change how kubelet mounts volumes generally, this is a pretty big change on its own. It would demand a different cap that would, again, need to graduate to alpha and beta and GA, and it would block us seriously. And yeah, this was one of the moments that I said to myself, maybe this was a bad idea. Maybe I'm not sure how we can even solve it. And doing another follow-up, another cap that would be our dependency is really horrible. But then a kind of a miracle happens, and tempfs has these options, right? You can provide options to it, and turns out that there is a really new option that's called NodeSwap that exactly fits our case. So that was amazing to see. But it had a problem as well, because, as I said, it's very, very new. So it's not supported on every node. So basically, it's supported only on kernels versions that are above 6.4, and that's sort of correct, because upstream on the Linux kernel, that's what's going on. But the distributions can choose to backward it to older versions, and that's basically what all of the distribution is doing. So what we decided to do, and that's a comment from the actual PR, and only the last row matters here, is that what we'll do is try to detect if the no swap option is supported. If it is, we'll use it and everything's fine. If it's not supported, we'll prompt a warning, but we will continue either way. And the thing is that, so first of all, how do we know if it's supported or not? So if the kernel version is above 6.4, then we're fine. If it's not, kubelet will try to mount a dummy volume and see if it gets an error for like unrecognized option. If that will happen, then it's not supported. But the key thing to understand here about that is that that's a very temporary problem. Eventually, and when I say eventually, I mean the very near future, it will be widely supported within everywhere, basically. So that's how we solved it and got away with it. So this is great. So the current situation. Swap was reached alpha in 1.22. We were able to graduate it to beta 1, which is like sort of like half beta in 1.28. It reached full beta in 1.30, and the intention is for it to GA in 1.32. There's and there is a pretty broad consensus that it will. So fingers crossed, but I'm pretty confident about it. And I think I'm very happy about it because 4 releases to reach from beta to GA. With all of these challenges, I think it's lightning speed for Kubernetes perspective, so I'm very happy about it. And now there is massive interest about it. So many companies are really interested in it. Intel just gave a KubeCon talk about it. And Google, NVIDIA, Facebook, tons of companies are very in favor of this. In Kubernetes sig-nodes, it has the highest priority that a cap can have. So again, it's become from something that nobody cares about to something that it's really important. And the follow-up caps are not ready yet, but they are work in progress, and they will be introduced soon. I think that this is important because this is the perfect time to get involved. We are just past beta. We are just before GAing. This is a great point of time that you can share your use cases with us, feedbacks, criticism, whatever, everything that's on your mind. You can message me specifically on Slack or on Kubernetes sig-node or our dedicated channel sig-node swap. And yeah, by doing so, you can pave the way that swap will be implemented. That's just the perfect time to do so. Yeah, so this was everything. I'm the swap out here, and if you have any questions, That's the time. So yeah, any questions? Yeah, okay, so there is, the question was, how can we prevent stuff that are outside of kubelet's reach, basically, to use swap? And the answer is that you can do that, but kubelet can't do that for you. Because kubelet is owning only their subtree of the cgroup, right? And they're basically are responsible only for the processes that are created by kubelet. However, you can do that on your own, right? So that's basically, you should look at the best practices that we have on the CAB, because there are a lot of interesting stuff like that are pretty important. Yeah, so I mean, everything that outside of kubelet's reach, kubelet just cannot do. You can, for example, in the system slice, define memory swap max to be 0. But there are more interesting stuff that you can do. So, for example, I/O latency is an interesting one, because when a lot of processes are swapping, it could affect the I/O latency of critical processes. So, one of the best practices is actually giving priority for the system slice for I/O latency. So, yeah, you can find more information in the CAP itself. Any other questions? Okay, thank you very much. Have a great rest of the day.